My name is Chiara. I work for European Bioplastics, and this is a series that we have been running for a year now. We call this series Touchbases with novel research and innovation projects focusing on bioplastics from different angles. So we are looking at bio-based materials, we're looking at biodegradable materials, and we look at applications as well. This project is a bit special because it's kind of phasing out, so it's more mature than the other ones that we presented before. And I think this is making it very interesting also for those of you that are working in an industrial context, maybe for a scale up. So just to give you a little bit about this framework of today, we are running for 45 minutes, this format. I will just steal a couple of minutes more so that I can make sure that everybody is in the room and that everybody is understanding the scope of this format. This is a format for you to discover possibilities for collaborations. So with scientists, outstanding scientists, researchers, innovators, explore opportunities, meet eventually future project partners, future business partners. This is why we are organizing this once a month for 45 minutes. We are running this, it's under the several projects. So this format is fully funded by the European Union through different funds. This is why I usually put this disclaimer as well. And this is a way to say that we are not responsible as European Bioplastics. Only the author is responsible, not even his funding agency is responsible. Just go along with this. And this is for me a must to show. Few things that I would like to promote. I would like to promote two of the talks that we are scheduling for September and October. So we have them once a month. We go on holiday now for July and August. And then on the 1st of September, we have invited the Repurpose project. So they will be talking about recyclable elastomeric plastics, especially for specific post-consumer waste streams, recycling of post-consumer waste streams. And we will be talking with Sofia Kadar. And then we have a project that is focusing mostly on soil and also healthy soil, permanent crops, living labs. So the use of bioplastics also in soil with AREF, that is the European Assembly of Horticultural Regions. So if you want to put them in your calendar, I will also paste later the link to this talk so that you can register. Today, we are here to talk about the SuperBark project. So Mark, with his team, has been researching on safe, sustainable, and high-performance adhesives and coatings from industrial softwood bark. As I said, this is a more mature project, so there are still some plans to go, but the project is also ready to finalize the activities next year. And this is why we invited Mark from VTT to join us and to explain a little bit more what he does and what they achieved as a group. And this is where I stop my sharing.
Thank you, Chiara. Thanks for inviting me to talk about SuperBark today. Good afternoon, everyone. I'm located in Finland, so I already had my lunch. That's why I'm saying good afternoon. I guess that many of you are in Central Europe or Southern Europe, so then probably it's still sort of morning to you. My name is Mark Borrega, and I'm working at VTT. For those of you not familiar with VTT, this is the Technical Research Center of Finland. It's a large institute. We are over 2,000 employees, and we do research on many topics, from materials development, chemistry, networks and communications, nuclear safety, whatnot. I think maybe medical sciences is probably one of the only disciplines that maybe we don't really do research on. But in my case, I'm working as a principal scientist and project manager on topics related to development of biorefineries, biorefining processes, and bio-based products. So today I'll be presenting the SuperBark project, which as Chiara said, has been running for a while, close to 3 years, and we still have 1 more year to go. Yeah, so to start with, I'll give some general information about the project. So as said, this is a project that started already in September 2023, and it will end in August next year. So it's a 4 years project. It's funded by the CBE-JU. We have a budget of close to 4.5 million euros. And we have a consortium of 12 partners from 8 different European countries. I think we're quite nicely distributed across Europe. So we are 6 research organizations, 1 university, 1 SME, and 4 large companies, and VTT is the coordinator. So there in the map you can see VTT, Metsä, and Click from Finland. We have Riga Technical University from Latvia, Horsforschung Austria, and Adler coming from Austria, Kastamonu from Turkey, Tecnalia from Spain. Then we have Pulp and Paper Institute and Goricane, both of them from Slovenia, List from Luxembourg, and Fraunhofer from Germany. So this is who we are. And before getting into the actual project, I thought I would just briefly show why are we working on this project. What was the motivation to apply for this? Being located in Finland, so Finland, in Finland or in the Nordic countries as well, like Sweden, the forest industries are very large and relevant for the national economy. So there's a lot of forest activities, and bark is a side stream which is generated during the debarking of the wood logs to make different type of wood products, pulp for paper, and so forth. So and there's a lot of it. In Europe, there is more than 12 million tons dry of industrial softwood bark. So this is only bark from softwoods. Softwoods are coniferous species. And this is actually one of the main or most abundant side streams from the forest industries. As I said, the majority of them are generated in Sweden and Finland. Typically, what's done when the bark is generated or let's say obtained at the mills is that they burn it for energy. This energy then is used for heating, for electricity, for steam. But this is a relatively low value. It's energy value, which of course is not it's not a waste, but it has a relatively low value. And when we consider the chemical composition of the bark, so there are some interesting compounds. There's, for example, tannins. Tannins are polyphenolic substances. These are interesting because they are not typically found in wood, at least from most European species. But we also have relatively large amounts of cellulose. So this could be, we believe, utilized in different applications which would have a higher value than just burning. And in this project, in SuperBark, we are concentrating on making adhesives and coatings. So these are the 6 main objectives of SuperBark. So we first produce bio-based components from industrial softwood bark. Then we use those components to develop adhesives and coatings, both of them having more than 95% bio-based content. And the adhesives are to be used in the manufacture of wood panels. The coatings are used for wood panels like plywood, but also for packaging paper. All these developments are or guided by a safe and sustainable by design assessment. We also do techno-economics and other type of modeling. So we apply digital tools to support the developments, the scale up, and eventually the market integration. And of course, as part of all EU-funded projects, so one of the main objectives is to communicate, disseminate, network, and exploit the outcomes of the project. So these are the expected impacts. This is actually taken from the call text and adapted to SuperBark. So the main impacts that we are targeting in this project are to increase the bio-based product portfolio by developing different types of adhesives and coatings. We are also targeting to improve recyclability of the end products like packaging paper and the wood panels, improve the sustainability, for example, by using natural side streams and raw materials like bark into as raw materials for the development of these bio-based solutions. And last but not least, this is one of the most important impacts of the project, is that we want to improve the health and safety of workers and consumers by mostly targeting to replace fossil-based chemicals, for example, formaldehyde-based resins or adhesives, which are used in wood panels, as well as, for example, PFAS used in packaging. Okay, so this is just a snapshot of how the whole value chain looks like and what we are doing in the project. So from left to right, we start with our raw material, which is the softwood bark, a side stream. Then we do an extraction process, which is patented at VTT. It's an alkaline extraction, and this basically separates the bark into two main fractions. We have a liquid fraction, which is rich in polyphenols, for example, tannins. There's also some lignin. This we recover by applying membranes. And then the other fraction that comes after this alkaline extraction is cellulose-enriched bark residue that we use to make cellulose nanofibrils by a mechanical fibrillation process. So if we look at the upper value chain, let's go back to the polyphenols. So these are then used as building blocks to formulate different types of adhesives for plywood, particle board, and MDF. Those are different types of wood panels. They are also used to make some coatings, as you will see. And then the nanocellulose is used as an additive or as an ingredient in coating formulations for this packaging paper, particularly to bring barrier properties and also for wood panels. And as I mentioned before, so this is all guided by the safe and sustainable by design, different types of process modeling, and we are also supported by our communication, dissemination, and exploitation partner. So now I'll be showing you what we have been doing in some of these, let's say, main work packages or technical developments. Let's start with the production of bark-based components. So this is basically how it looks like. I was just saying it, but now maybe it's easier to see with images. So we start with our industrial bark. In this project, we work with 3 different types of bark, from Norway spruce and Scotch pine, which is found in the Nordic countries, and then we have bark from Calabrian pine from Turkey. So we do this alkaline extraction, we get this extract rich in polyphenols, which are then recovered by membrane filtration. But the membrane filtration is one of the main things that we have been researching and studying in this project. We also do some acid precipitation as alternative. Then the bark residue, which is enriched in cellulose, is fibrillated, and you can produce this type of hydrogel, which we call nanocellulose. And since we have still lignin and residual polyphenols in the bark residues, so you can see that the bark-based nanocellulose has still this brownish color. Now, what do we do with those components? So let's start with the adhesives. We take these bark polyphenols as dry powder, and we use those in different formulations with different cross-linkers, different solvents to develop. In SuperBark, we're actually developing 4 different adhesive formulations by different partners. And each of those formulations is targeted to a different type of wood panel because they have different requirements. And also each wood panel could have different requirements depending on the intended use, whether it's indoor or outdoor. The requirements for the adhesives and for the final products are obviously different. So we develop different types of resins that then we apply to make this, we test in the making of plywood, this MDF and particle board. As I mentioned before, one of the targets of the project, which is in alignment with the requirements of the call, is to develop these formulations which are at least 95% bio-based. And the target is to replace fossil-based resins, mostly phenol formaldehyde and urea formaldehyde resins, which are the benchmark reference adhesives or resins used in this type of panels. So basically now we're going to reach year 3. So we have been testing, developing and optimizing most of these formulations, or all of these formulations actually, in lab scale. And now we are at the point of validating some of them at higher tier level in collaboration with our industrial partners. Now, these polyphenols can be used not only to make a resin for adhesives, but also for coatings. This is an example of the coatings developed by our partner from Holzforschung, Austria. So basically, they have developed a resin which is 100% bio-based. They use the polyphenols and a bio-based cross-linker. It's you can see in the middle image there's like a liquid, brownish liquid, which is the resin. And for this type of coatings, for the plywood coatings, this is called paper impregnation, and so it's an overlay paper which is pressed onto the actual wood product. So you have a paper, you impregnate it in this bark-based resin, and then you put it on the plywood, you press it, and you have this brownish coating. And this is actually it performs very well. So we in this project we are targeting at coatings for transportation applications for plywood, which have a very high demands in terms of abrasion and scratch resistance, also in terms of hardness. And these coatings actually are performing very well, complying with the requirements needed for this type of application. And this could be a very good substitute for phenol formaldehyde resins, for example. How are we on time? Okay. So the other component, so we have now seen the polyphenols. The other component that we are exploiting in this project is the bark-based cellulose nanofibrils. This is used to make as an additive for different types of coatings. Here I'm showing for how it's been used for wood coatings. Again, this is a work done by Holzforschung Austria in collaboration with Adler. So you start with the bark-based nanocellulose. Since nanocellulose contains a lot of water, the dry solids content of this nanocellulose is, if I remember correctly, something around 3%, 3-5%. It's a bit higher. It has a bit higher solids content than typical wood-based nanocellulose, but still contains a lot of water. You don't want to bring a lot of water into the coating formulation. So for that reason, we have been dehydrating this and making sort of a paste material, which is then used, as I said, as an additive in a solvent system to make these wood coatings. And what we saw was that additions of just small amounts of this bark-based nanocellulose can actually help improve the scratch and abrasion resistance of the coating wood. So this could be, for example, utilized in different types of flooring or other applications in which you require this scratch and abrasion resistance. This is still work in progress, but so far we're having some nice results as well. Now we change the end product. So far I was showing the adhesives and coatings for wood. Now we are looking at making coatings for packaging paper, also using the bark-based nanocellulose as an additive. But in this case, we use a bleach bark CNF. This is done by taking the bark residue and before doing the fibrillation into nanocellulose. So we do a bleaching process to remove some of the or most of the residual polyphenol. So you can see that it clearly has a whiter color than the starting nanocellulose. So in here we have also used the unbleached nanocellulose, but the bleached nanocellulose works the best. So this is added in a formulation containing another bio-based polymer, and after mixing, you use the formulation to coat packaging paper. The work has been done or is being done by our Slovenian colleagues from Pulp and Paper Institute in Ljubljana and Goricane. They're working together on this. They have been measuring all the barrier properties which are relevant for the final application, which is food packaging. And they have been testing oxygen transmission, water vapor transmission, grease resistance, also mechanical properties. So far, after a lot of optimization, they have come up with a formulation that complies also with the requirements of the coating for food packaging. And this is done in lab scale. Now the next step is the scaling up. This is another type of let's say, rather than a coating, we have been working on using this nanocellulose to make films, for example, to replace different types of plastic packaging. We have been using bark residues with and without bleaching. So we wanted to see what was the effect of this polyphenolic content in the actual nanocellulose. So from the nanocellulose, we mix it with a plasticizer, and then we do casting. And after drying, we make these self-standing films that you can see there on the right. They're smooth, and they're like homogeneous and continuous. So VTT this is done by VTT. VTT has a lot of experience in making this type of films from nanocellulose. And this is quite interesting because you can also tune the color of the films. They look quite nice depending on what is the polyphenol content. And we have also measured barrier properties, strength properties, and basically what we see is that they have properties comparable to the ones that you would get if you make a film from wood-based nanocellulose. So I would say that in that respect, they do not, having this bark-based nanocellulose film does not bring any performance advantage, but it can has the advantage of using bark as a side stream rather than using the wood pulp. So coming closer to the end, so as I mentioned, we do all the developments guided by the safe and sustainable by design. We also look at techno-economics. So all the chemicals, all the materials that we use are screened for safety. The ones that are, let's say, flagged with having some issues, then we look for alternatives. We are also doing the sustainability assessment by LCA. That is done for all the value chains, for coatings, adhesives, for the different types of wood products. So it's quite a lot of work. We also do techno-economics, mostly for the production of the bark-based components, and there we consider different scenarios for the production of these bark-based components. For example, we consider the scenario that the pulp mill that has the bark would do the alkaline extraction and would produce the bark-based ingredients there on site. Then another scenario is that this bark would be sent somewhere else to a standalone mill where they would do this extraction. So we're looking at different things and different scenarios for the production of the bark-based components and looking at the economics. So what is the outlook for the last year of the project? So now basically we have been working very hard to test, develop, and optimize all the different formulations. We have done the lab work to mostly. So now the next year will basically focus on validating those formulations which perform the best in, let's say, semi-pilot scale, like TRL5. We are also planning to build larger samples that we can use as demonstrators, but also, for example, for recyclability studies, which is one of the things that we want to demonstrate in this product. We're also looking at biodegradability. Then we need to finalize the LCA with the selected solutions for each value chain, and of course all the communication, dissemination, and planning and updating the exploitation of the results. So with this, I think I've covered my time. So this is a picture from the last consortium meeting in March in Germany. Thank you very much for your attention.